Hello, I'm Joonwoo, Group Leader of Quantum Information Theory at KAIST. I'm happy to introduce our research group and our research activities. Let me first introduce myself. I have academic background in both mathematics and physics. Firstly, I started from mathematics. When I was finishing the degree, that was around 2000, everyone started to speak about quantum algorithm, in particular quantum prime number factoring algorithm. Then people also started to address its impact in science and industry. With my background in number theory from mathematics and quantum mechanics from physics, I tried to follow the paper about quantum prime number factorization. I spent a few days, but my understanding wasn't perfect, but I thought, okay, I can do it. That was the motivation I applied for PhD in the European Union Center, ICFO, which was in Barcelona. And then I started to study quantum algorithm and quantum cryptography. The main topic of my PhD was the security proof of quantum cryptographic protocols. Then I worked in KIAS, Korea Institute for Advanced Study, and CQT, Center for Quantum Technologies in Singapore, and FRIAS, Freiburg Institute for Advanced Study, and Hanyang University. Now I'm currently working in KAIST EE, Electrical Engineering. The main motivation to quantum information technologies may be found in this picture. We now enjoy the information technology industry. Before that, there was a fundamental theories about computing and communication. And before that, there was a fundamental physics, electromagnetism. That was a fundamental physics that defines bits. So electric signals on and off, and that defines the unit of information processing, which we call bit. The current IT industry may reach its limitations, which we call the Moore's law. It means that there won't be a dramatic improvement in hardware. But we want to develop software given that hardware. The biggest achievement after electromagnetism in fundamental physics would be quantum theory. There was a theory about microscopic system. Then, if you see the history, as electromagnetism leads to the IT industry, you can expect quantum IT industry in the future. So now may be the right time to develop information technology based on the laws of quantum mechanics. What would be quantum computing and what would be quantum communication? The first line of our research activities is to pioneer new quantum information applications. We are primarily interested in quantum cryptographic protocols, in particular security in a realistic setting. Devices in quantum cryptography, actually they are not yet perfect. They show loopholes in security. We want to close it. We want to solve the problem. We want to achieve a higher level of security. We also want to move a more general setting, a network communication. There, we want to exploit quantum resources, for instance, entanglement, non-locality to network protocols, such as interference channels and multiple access channels. And then our goal is to achieve higher channel capacities. We are also working on new quantum algorithms. We generalize quantum database searching algorithm. We also realize a quantum prime number factorization algorithm. In fact, today's quantum technologies, noisy intermediate scale quantum systems, they are also not perfect. They contain noise in all of the steps of information processing. We also develop quantum software to prescribe the problems of today's quantum hardware. For instance, we are working on quantum tomography for the verification of quantum states, dynamics, and measurement. We are also working on dealing with quantum errors. For instance, how to mitigate the errors and how to remove the errors, how to detect the errors and correct the errors. All these describe the interactions between system and environment. The engine that allows us to proceed to quantum technology is our basic understanding on the fundamental physics and fundamentals of quantum information theory. We work on quantum measurement for the characterization of realistic devices. And entanglement means kind of correlations that do not have a classical counterpart. And if two systems share entanglement, one can achieve non-local correlations. So non-locality may be found as a consequence of entangled states. We deepen our understanding on these fundamental quantum resources. Overall, we interplay quantum foundations, mathematical tools, and their applications to practical quantum information processing that includes quantum computing and quantum information protocols. The research group is with a research professor, postdoctoral researcher, and 10 students. We also collaborate with our colleagues in the world, the US, Canada, Europe, and Asia.